Welcome to Introduction to Quantum Field Theory, Lecture 7. In this lecture, I will provide more of an interpretation of quantum mechanics as a path integral and also provide a roadmap to formulating quantum field theory using a path integral representation. For reference, please have a look at the textbook, Chapter 6. Where do we stand? On the one hand, we have quantum mechanics. Quantum mechanics involves operators, wave functions, eigenvalues, and solving differential equations, such as the eigenvalue equation for the energy eigenvalues. Once we have those eigenvalues, we can use quantum mechanical information to calculate observables, such as the quantum mechanical partition function, which turns out to be just the sum over the exponential of these eigenvalues. On the other hand, in this lecture, we have explored a completely different setup for observables in quantum mechanics, namely the path integral representation. In this representation, the quantum mechanical partition function is written as an infinite dimensional integral over an exponential involving a purely classical object, this Euclidean classical action. Note that in this representation of quantum mechanical observations, there are no operators, there are no eigenvalues, and there are no wave functions. All the elements that are needed to set up the observables are purely classical. There is just classical information that goes into this description of what quantum mechanics actually is. The heavy lifting is provided by the infinite number of integrals that are in the path integral representation. Now, the main point to realize is that the path integral and the sum over the eigenvalues lead to the same result for this quantum mechanical partition function. This is not a coincidence. In fact, the classical path integral and quantum mechanics are identical descriptions of the same physics. So far, we've talked a lot about the partition function that, to some of you at least, will seem to be more a concept in statistical mechanics than quantum field theory. However, I want to show you that this has a lot to do with quantum field theory. In particular, we want to sort of study a quantum mechanical object, such a transition amplitude from a position x prime at time t prime to position x double prime at t double prime. This matrix element here can be sort of written in terms of a path integral using steps that are very similar to the ones that we've used to write down the partition function. Particularly, we can factor out the time dependence of this matrix element by using the time evolution operator, such that the matrix element can be written as a matrix element between two position states, x and x prime, and a Hamiltonian that sort of describes our time evolution. The main point is that this matrix element is very similar to the matrix element we cast in terms of a path integral. First, have a look at the exponential. The exponential involves the Hamiltonian operator in both cases, the only difference being that for the partition function, we have an inverse temperature called beta in here, and for the transition amplitudes, we have I times a time difference here. So you can see that these two exponentials are analogous to each other when we replace the imaginary time tau by I times the real time t. Also note that for the transition amplitude, we have a different position state on the left and the right, whereas for the partition function, we had the same state x on both sides of the matrix element. So we'll have to sort of change these differences. And we also have to take into account that for the partition function, we had a trace, meaning an integral over all positions, whereas this doesn't occur for the transition amplitude. The path integral for the partition function we could show to sort of be given by an integral over the exponential of the Euclidean action with this periodic boundary condition, x of 0 being x of beta. Some of these concepts and results are similar when we sort of derive the path integral transition, the path integral for the transition amplitude. First, note that we go to real time, so we replace tau by it, which means that the integral over the tau turns into integral over t. The second thing to notice is that because we had these two states at the two positions to be the same, this involved, or this led to this periodicity condition, x of 0 is x of beta, and that informs the integral limits of the imaginary time integral, the tau from 0 to beta. For the transition amplitude, that's different. There we have 2 times t prime and t double prime, which now give us the limits of our integral over time. Also, at these 2 times, the value of the positions that we insert are no longer the same. They are sort of given by x prime for the right-hand side and x double prime for the left-hand side of this matrix element. Following exactly the same steps that we used to get to the partition function, we can write down a path integral representation of this quantum mechanical transition amplitude. And it sort of looks like this. We have a divergent but constant factor in front. Then we have an infinite dimensional integral over position space times e to the I integral over real-time t times L, where L now here is just the classical or Lagrangian of a point particle. This goes together with the requirement that at these endpoints, meaning x of t prime, we have the same as the matrix element on the right-hand side, x prime, and x double prime on the left-hand side. So basically, that informs the statement that the quantum mechanical transition amplitude and the partition function are analogous. They have some difference, though. The transition amplitude is a real-time object. It carries real-time information about how one state transforms to another. As such, it's formulated in Minkowski spacetime, and its path integral has an I in the exponent. So it's a path integral over e to the is, where s is the classical action. Because this exponential is not real, the path integral is somewhat ill-defined mathematically. It's possible to basically provide rigorous mathematical footing for this expression, but it's certainly more tricky than what we had for the partition function. For the partition function, that object carries information about the thermodynamic equilibrium. It is formulated in Euclidean spacetime, and it's a path integral of e to the minus se. Because all the integrals are essentially falling exponentially for large values of the fields, all steps of this path integral are well defined mathematically. So we can talk about different sort of discretizations of the path integral. All of these are well defined. So from that point of view, it is a much better behaved object mathematically. Also, because this action here in the exponential is purely real, it is possible to calculate observables, such as the partition function, via Monte Carlo importance sampling of an infinite dimensional integral. This really opens the door to being able to use brute force method supercomputers to calculate first principles quantum field theory information. And this is not possible in general for transition amplitudes that suffer from non-real actions. What is the path ahead? So now that we have some understanding of how quantum mechanics involving operators, wave functions, and so on map into a path integral representation of quantum mechanics, we can use that knowledge to sort of try to provide an idea of how we will formulate a representation of full quantum field theory. To reiterate, for the setup of quantum mechanics as a path integral, what we used was classical Lagrangian mechanics, where we have a Lagrangian and an action that's just the integral over that Lagrangian. To go from classical point particles to fields, we will change the coordinates. So instead of having positions, we sort of will talk about fields that depend on positions. As such, we don't have a Lagrangian, but we'll have a Lagrangian density. That's denoted by this calligraphic L. And we'll have an action that is given as a volume integral over this Lagrangian density. Quantum mechanics was set up by just using the fact that we have classical Lagrangian mechanics, writing down exponential of minus the action and letting the path integral, the infinite dimensional integral over the fields, do the heavy lifting to give us a quantum mechanical object for the partition function. Essentially, we can exploit this and write down an expression for quantum field theory that follows exactly the same idea. So given a Euclidean Lagrangian density, we will write down an action that involves the integral over this Lagrangian density, and then there will be a path integral that is just an integral over all the possible field configurations to define a quantum field theory expression for the partition function. This concludes today's lecture.